I told you a few days ago that Physics 12, the first third, is a review of Physics 11. The big difference page is we're going to be emphasizing vectors much more. So this is an introduction to the mathematics of vectors. Recall, in physics, all measured quantities are either something that begins with an S or something that begins with a V. Scalars or vectors. Oh, highlighter off. In Physics 11, it was easy to be casual whether it was a scalar or a vector because I really wasn't giving you that much directional stuff. In Physics 12, though, you are going to want to memorize which ones are scalars and which ones are vectors. Now, you know that I hate memorizing stuff, Kira. You're not going to need to make flashcards. I'll just keep emphasizing it, and if you keep up with the lessons and keep up with the homework, you'll just naturally memorize which ones are which out of sheer repetition and laziness. So don't think like you need to make a flashcard list or something like that. Vectors have magnitude only. Based on that short video clip, you would say vectors have both what and what?
Magnitude and direction.
Magnitude and direction, or direction and magnitude. I'll go magnitude and direction. So let's look at Patrick the puppy. Patrick the puppy goes wandering around his neighborhood as seen below. Let me zoom in so you can see a bit better. So he starts at the front porch. It looks like he goes north for a while, stopping at various bushes to pay them some attention. Then he goes east for a while. Then he goes here, stops at the fire hydrant, and then he comes to a complete rest there. There are several ways that I can describe Patrick the puppy's path. Notice there are a series of arrows drawn on the map of the physics teacher's front lawn. Each arrow shows the magnitude and direction of a series of successive trips made by Patrick the puppy. These arrows, showing both magnitude and direction of his displacements, are called vectors. When Patrick the puppy reaches the final spot near the car door, how far has he walked since he left the porch? Kira, it depends on what you mean by how far. Distance is the number of steps, and if you want me to do the distance, I would say, well, it looks like it's 3 meters plus 2 meters plus 4 meters plus 4 meters plus 2 plus 4, which is what? In your head or on a calculator, I don't care.
19.
Can someone confirm? Because he did the 19, but Ben just echoed him without doing it in his head because he wanted the glory. Is it 19? Yes? 19 meters. The displacement is a bit trickier. The displacement is this arrow here. Now, how the heck could I get that? Well, I guess I could superimpose a little triangle on this arrow here. So here's what I want. This is the displacement, and I'll put a vector symbol above the D. How long is the base of this triangle? How long is the base of this triangle? How'd you figure that out? And I'm just going to say, figure it out. You'll have enough information in the diagram to move lines around and get that. How long is the vertical part of this triangle? I don't think it's 7. 3. And so I can find the magnitude by using Pythagoras, which is what? By the way, this is the 3, 4, 5 triangle. I think if you do this, you'll go 4 squared plus 3 squared equals, and you'll get 25, and then when you square root, you'll get 5. So I think the magnitude of the displacement is 5 meters. But now we need a direction because displacement is a vector. To show that we're about to write a direction, we typically write an @ symbol, the shift 2 on your keyboard, the symbol that goes in your email address. I have a real tough time as a lefty drawing that, so you're going to see it just gets messier and messier and messier. Sometimes it'll just look like my pencil threw up on the page. Trust me, that's probably meant to be an @ symbol. Well, we have this angle here is 53 degrees from the picture. Now, problem, I want the angle inside this triangle. Oh, wait a minute. Not a problem. What do these two angles add to? 90. So if you go 90 minus 53 on a calculator in your head, by the way, I typically do angles in my head in my homework, but when I've been doing angles like subtracting from 90 on a test, I've forgotten to carry the one so often, I swallow my pride, and often on a test, I will go 90 minus 53 and type that into my calculator just to make sure I don't make a dumb mistake and say 47 when I clearly meant what?
37.
37 degrees. However, that's not a direction yet. If we superimpose a compass rose here, we would say that this is 37 degrees north of east. 37 degrees north of east. And I know that right now you're going, where the heck did you get that from? We'll practice that in a second. But typically, if we're giving a direction, there is an angle theta and a something of something. South of west, north of east, east of north. Little note, there are two ways to indicate that a quantity is a vector quantity. In diagrams or in handwritten notes, we draw a small arrow. So I really should have done this, Mr. Dueck, if I was really, really clever. I would have gone D with a vector sign equals to show you that it's a displacement. We draw a small arrow, really a half arrow, above the quantity. In textbooks, the symbol for vectors is often bold italics, but to handwrite that is tricky. In other words, to handwrite a bold italicized D, I guess I'd kind of have to do that. Well, that's dumb. So when we're handwriting vectors, if I want to show you that it's a vector, I'll put a symbol, a little arrow above it. In a textbook, you would just see a bold fonted capital F. If we just want the magnitude, so even though it's a vector, if the question just asks how big, I don't care about the direction. If we just want the magnitude, we often use absolute values. So if I just wanted the magnitude of the displacement, I used a lowercase d, so I'll do that, and that would be 5 meters. So, scalars and vectors. If you add 3 kilograms of sugar to 2 kilograms of sugar, you get 5 kilograms of sugar. If you add 3 liters of water to 2 liters of water, assuming you don't let any evaporate, you get 5 liters of water. Masses and volumes are added together by what you think of as the rules of ordinary arithmetic. They're scalar quantities. Scalars have magnitude, but they have no direction, much like your futures. So, other scalar quantities include, anybody remember some scalars from last year? Speed? It would be nice if there was a dumb way that I could remember that speed is a scalar. If I was a good teacher, I'd have a way for you to remember that speed is a scalar. I got nothing. You'll have to come up with something on your own. What else? Scalars. One that came in really handy and will come in handy again this year is work or energy. That will allow us to use it to analyze roller coasters, because if we used a vector approach to try and analyze a roller coaster, every time the hill changed its direction, we would have to be doing some heavy-duty math, and it would get ugly. So especially if you look at it from the side, you're going to hear me say if it has a yucky, curvy path, that's often a job for conservation of energy because it's a nice scalar approach. Other scalars, distance versus displacement. Distance was a scalar. Let me think of some. Well, voltage will be a scalar this year. This doesn't mean that the numbers can't be negative. It means a negative number for these means you're losing energy or you're losing voltage. That's all. However, if you add a 3-meter displacement to a 2-meter displacement, the two displacements together might add to 5, but they might add to 1, or any possible value between 5 and 1. So this shows some ways these displacements might add up. You could go 3 meters right plus 2 meters right. Well, that's 5 meters to the right. You could go 3 meters to the right plus 2 meters to the left. Well, that's 1 meter to the right. You could go 3 meters right plus 2 meters up, and that's going to give you a displacement of 3.6 magnitude. I didn't include a direction. Hey, you could go 3 meters this way and 2 meters that way. What the heck is that going to be? We'll talk about that. These vectors are added by the rule for vector addition, and that's the theme of today's lesson. As you can see, the resultant displacement depends on the directions of the vectors as well as their magnitudes. Other vector quantities besides displacement. Who remembers some things that were vectors last year? Who remembers some things that were vectors last year?
Velocity.
Really? Velocity is a vector? It would be great if there was a dumb way that I could remember that velocity is a vector. I got nothing, so you'll just have to remember. You can write the word velocity. I chose to use the symbol. I tend to abbreviate. What else? What did capital F stand for?
Force.
Force is a vector. It matters which way you push on something. Okay. Acceleration is a vector, although this year we're often just going to find the magnitude because we'll have more than one object accelerating, and they'll be accelerating in different directions. They'll be attached by a string, but one, like in the Atwood machine, one moving up, one might be moving down, so we'll just get the magnitude. Momentum was a vector. In terms of new stuff this year, electric field, you'll find, is very much a vector, and direction makes a huge difference. Magnetic field makes it. Magnetic field, that will determine whether the magnets attract each other or repel each other. Direction matters. If we add together force vectors of 7 newtons and 4 newtons, what's the maximum magnitude of the force that I can possibly get? What's the biggest it can be? Nat? Yep. What's the smallest it can be? In your head? Nope. Smallest magnitude, so we don't care about negative direction, just smallest magnitude. What's the smallest you can get? 3, yeah. And then, if they're not in a straight line with each other, you can get every possible decimal value combination in between 3 and 11. I brought out this weird 37 degrees north of east. Turn the page. Let's talk about how that works. How do we write vector directions? I'm going to strongly recommend, those of you that have had me before know I'm lazy but organized, but if I can spend 1 second reducing a bunch of dumb mistakes, I will. I'm going to strongly recommend anytime you start to do directions, put a compass rose somewhere on the page. So the first thing that I'm going to do is I'm going to go north, east, south, west. I am the king of mixing up east and west. I just do it all the time. Don't ask me why, but I do. So I will prevent that. I'm going to zoom in to this 28-degree triangle. And it asks, what direction are the following vectors? Now, because I've zoomed in, I've just lost my compass rose, so I'm going to put it right here so I don't do something silly. You will notice that this vector is made up of a slanty line and a non-slanty line. Okay? I'd like you all to write 28 degrees. What direction is the non-slanty line pointing? East. What direction is the slanty line pointing? North and east. So the real question is this 28 degrees east of north, or is this 28 degrees north of east? The rule is the non-slanty line goes after the of. So leave a space right here and write the word of east. And then if you'll notice, what direction do I need to go from east to touch the slanty line? North. This is 28 degrees north of east. This one here is 51 degrees north of south, east of west, what of what? So I see two lines. Which is the non-slanty line, the nice line? Which way is it pointing? So it's going to be of north. And from that north line, which way do you have to go to hit the slanty line? This is 51 degrees east of north. This is the direction convention that we have come up with in physics. 20 degrees north of south, east of west, what of what? So this is going to be 20 degrees of what? What comes after the of in this case? The nice line. And if you're looking for a dumb way to remember, you can finish, there's an expression, nice guys finish last, nice lines finish last. They come after the of if you're looking for a dumb way to remember it. So it's going to be of north. What of north? West of north. "48 degrees north of south, east, north of south, east of west, what of what?" South of west. Start out going west and then go south of west. "78 degrees north of south, east of west, what of what?" West of south. By the way, this is kind of tricky. I'm hoping you'll understand this. One of the smartest students I ever taught was a basketball player about, oh good gosh, 12 years ago. His name was Dylan Gattner, really strong student. He could not figure this out, and so he just memorized all 16 possibilities. He asked me to draw it out one time for him, and so I labeled each possible combination of where the slanty line or the straight line could be, and he memorized it, and that was his way of doing it. But it's better to wrap your brain around this. One more. 52 degrees. What will that be? South of east? However, each of these can be written in a different way. Every direction can be written in two different ways. It depends on which angle you chose to focus on when you drew your triangle. If I go to this first one, how big is this angle right there? Well, what do both the red angle and the 28 add to? 90. So this is 62. And so someone else, instead of saying 28 degrees north of east, they might have said 62 degrees east of north. Both of those answers I would mark correct. Both are equally valid. So you're going to often see in my answer key, if I ask you to find a direction, I'll have both of them there, because it just depends, Jagger, on what order you chose to start drawing your lines. When we start making diagrams from scratch, you might draw this line first and then that line. Somebody else might draw that line first and then this line. You'll get the same resultant, same magnitude, and you'll get the same direction, just a different reference, but it's the same spot. So what's another way to write 51 degrees east of north? 39 degrees north of east. Same answer. Another way to write 20 degrees west of north is 70 degrees north of west. And that would be if you were talking about that one there. Gets you to the same spot. 48 degrees south of west is the same as 42 degrees. What of what? North of south, east of west, what of what? And that would be that angle there. So you're noticing, oh, the letters just swap location, the directions swap locations, and then the angle is, in math, we call it the complement. It adds to 90. Two angles that add to 90 are very complementary. Is that a stretch or? No, in our notes, put it so you know what the heck we're talking about, why we're suddenly writing two answers. But no. I often will, remember my color. That's what I'll often do, but here I'm just doing the second one so you can see what the heck I'm talking about. So 78 degrees west of south, that would be the same as 22 degrees south of west. That would be if you started there and went there, and you can see Liam, you end up in the same location. This is why I always use a calculator on a test, because I often forget to carry the 1. Yep. Candy. Make sure I give you one at the end of class. Oh, my new students, anytime I make a mistake, if you catch me in it, you get a candy. So Mason gets one. Although he didn't bring a calculator. No, that's fine. 52 degrees south of east, 38 degrees east of south. Okay. So that's how we can do directions. Now let's put it all together. Let's talk about how we add vectors. Well, we did one-dimensional vector math last year. What's 5 meters east plus 3 meters east? Magnitude and direction. Magnitude. Direction. East. If they're in the same direction, you just add them and keep the same direction. What if they're in opposite directions? What's 6.2 newtons left plus 6.7 newtons right? 0.5 newtons. And then you could write the word right. If you wanted to and superimpose east, west, north, and south on here, I wouldn't freak out. In other words, if you said right is east, I would live with that too. The third vector, the answer, represents the sum of the two vectors. We have a fancy word for that. We call it the resultant. When you add two vectors or more than two vectors together, the sum of all the vectors is the resultant. And now you want to sit up and pay attention, because this is the new stuff. Adding vectors in 2 dimensions. Well, there's 2 ways to do it. We represent vectors with arrows. One way of adding vectors would be to carefully draw them to scale using graph paper and a ruler and a protractor. So, I'll have each meter be 1 square on the graph paper. And then you could carefully measure when you drew them the distance between, or better yet, we could use trig. So John travels 5 kilometers west and then 8 kilometers north. What's his displacement? Here is the rule, and it's in bold font. To add 2 vectors together, we draw them tip to tail. Sam, how do I add 2 vectors together? Draw them. Kira, I have a hankering to add 2 vectors together. Any suggestions on how I might want to draw them? Yeah. Ben, you know what? I feel like adding a couple of vectors. How might I want to draw them?
Tip to tail.
Tip to tail. Now, we're going to talk about what that means, but that's something you are going to have to commit to memory. That's not on your formula sheet. If I want to add 2 vectors together, I draw them tip to tail, and then the resultant is from the tail of the first vector to the tip of the second vector. So here's a vector. It says grab one. If I have another vector and I want to add them together, here's the tip of the first vector, here's the tail of the second vector. I would draw them tip to tail, and the resultant goes from the tail of the first vector to the tip of the second vector. Now, these ones are fairly difficult. We are almost always going to start off with right-angled triangles, and so I should have done that maybe to begin with, but we can handle it for anything. To add 2 vectors together, you draw them tip to tail, and you would get this angle right here by using SOHCAHTOA trig. You would use your second function sine, or your second function cos, or your second function tan button to find angle theta. And this would be, if this angle here, what of what? North of south, east of west, what of what? North of east. This would be north of east. Now, if I gave you those 2 vectors, and instead you drew this vector first, and then you added it tip to tail to that vector, you can see I get the same resultant, But here, you would be getting the angle that wasn't north of east. You'd be getting the angle that was east of north. This is why I said I'll always give you both thetas and both ways. I don't know what order you chose to draw them. Usually, I draw them in the same order that the question mentions them, because that's the most common. But sometimes that gives you a really yucky diagram, and so sometimes you'll say, actually, it'd be easier to draw them in the other order. So how do we add two vectors together, Paige? Draw them tip to tail. Chris, I feel like adding a couple of vectors together. Any thoughts on how I might want to draw them? Let's do some. So we have John traveling 5 kilometers west and 8 kilometers north. Have you all just turned the page? Draw compass rose. And what I typically do is I DULP. To my new students, this little word right here, DULP, stands for draw a little picture. So you're often going to hear me say, if you ask me a question, well, have you DULPed? Because that helps an awful lot, draw a little picture. So from the previous page, the two vectors were 5 west and 8 north. So I'm going to draw a vector that looks 5 west, like that. And I'll label it with a 5. And if you want to, you can put the kilometers on there. I'm not that fussy. And then I'll put a plus sign, because I do want to add these together. 8 north. Which way will I draw for north? Up. And I'm going to try and draw roughly to scale. 8 is bigger than 5, but it's not twice as big as 5. I'm going to kind of eyeball it. So to me, 8 would be, I don't know, about that big maybe. So I've DULPed. What's that going to equal? Well, Dan, how would I draw these two vectors and add them together? By drawing them. So it's going to look like this. 5. And then on the tip of the first vector, I put the tail of the second vector, 8. The resultant is from the tail of the first to the tip of the second. And since this is a displacement, I'm going to call it D vector for displacement. Now, there is a lovely right-angled triangle here. How can I find the magnitude of the displacement? I'm looking for something that starts with letter P. Yep. Okay. I'm going to write it in our notes. In your homework, if you are comfortable going straight to your calculator and giving me the magnitude, I'm good with that. But so that when we're studying, we know what the heck we did, I went like this. D squared equals 8 squared plus 5 squared. How do I get rid of a squared? Square root. This is the hypotenuse, so the D is by itself. So on my calculator, I would go 8 squared plus 5 squared equals square root, answer button. I'm going to go to 3 sig figs. When in doubt, go to 3 sig figs. I'm going to go 9.43. Units? Kilometers? You're not done. You've only found the magnitude. I'll put an @ symbol. I need to find the direction. Now the question is, Mr. Dueck, where do you put the angle theta? Top left or bottom right? So here's the next rule. The theta is always put where the vector is originating from. Theta is going to go right there. In this case, bottom right. It's where the vector is coming from. If you go back and look at the diagrams where we did all the direction stuff, that's what I was doing. How can I find the magnitude? Well, color. That 8, opposite, adjacent, or hypotenuse. That 5, which trig function? Tan theta equals opposite over adjacent. How do I find an angle? And please use your calculator to do it. I get 58 degrees. For angles, I typically go to the nearest degree. I don't always go to 3 sig figs. And the reason is 1 degree is about that big. You can barely see it with your eye. 0.1 of a degree, I'm not even sure you can see that with your naked eye, and I'm not going to be that fussy. Anyways, 58 degrees. In terms of work shown on a quiz or a test, if I see that, that's good enough. You don't need to then show me that you hit your shift button. I'll clue in. North of south, east of west, what of what? What's the nice line? Nice lines finish last. Of west. What of west? North of west. However, I would also accept 32 degrees west of north, and that would just mean you drew the 8 first, and then you went tip to tail and drew the 5 next. Okay, perfectly acceptable. Dan, in your head, what's 6 plus 4? What's 4 plus 6? When you're adding, does the order that you add things in matter, or do you get the same answer? When you're adding vectors, the order that you add things in doesn't matter. Dan, what's 6 minus 4? What's 4 minus 6? Did you get the same answer that time? When you're subtracting, order makes a difference. Later on, I'll show you how to subtract vectors. When you're subtracting, order makes a difference. Force 1 is 10 newtons due east. Force 2 is 6 newtons due south. Find the resultant. F with a little R for resultant. Hint, DULP. Okay. I've scrolled down, so I'm going to do another compass rose. So I want to add 10 east to 6 south. Yeah, that should be a little shorter. And again, I'm trying to be roughly to scale. 6 is roughly half as big as 10, so I'll make that line roughly half as big. Kathy, I want to add these 2 vectors together. Any thoughts on how I might want to draw them? Tip to tail, you say. So you're suggesting that I go 10 plus 6. And then, Kathy, the resultant is always from the tail of the first vector to the tip of the second vector. I'm going to freeze the screen. Can you please, on your own, find me the magnitude and find me the direction of this vector? I'll see if we get the same answer. Yes? No? Am I wrong?
You're probably right.
So I did Pythagoras, 10 squared plus 6 squared equals square root. You didn't get the magnitude. By the way, typically I'll make these worth 2 marks. 1 mark for the magnitude, half mark for the theta, and half mark for the what. So Make sure you do it all. Usually when I ask you a vector question and I say solve, I'll put in brackets magnitude and direction. Not always, though. So make sure you're reading the question carefully. Oh, and if you drew the 6 first and then you drew the 10, you would still get 11.7, but you would have got 59 degrees east of south. Why would you do that? Maybe in your paper where you had room to draw the diagram, you only had room to go in a certain direction just because of the way you've been filling up your paper, and you want to try and keep it on the same page, and you realized, oh, it's going to be easier to fit that diagram in if I go that way.
Is it always the lower number?
The smaller number here?
Yeah.
Nope. If you had drawn it this way, okay? Suppose you drew the 6 first, and then the 10. There's the resultant. Here's your theta, and it would be opposite and adjacent, and the 10 would be on top, the bigger number, okay?
So
Just,
the opposite number.
you can't memorize that. You have to do the trig. It'll usually be tangent, but not always. Just usually. I like example 6. I like example 6. I like example 6. Example 6 is a nice question. Paige, why would I say that? Did you hear me say it's going to be on the test? Or are you just the kind of student that pays attention and notices when your teacher emphasizes certain things? Good, 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 good. For my new students, that's a hint. If I ever say I like a question, that's a hint. I just turned the page, so I'm going to do a compass rose. A plane is flying due north at 132 meters per second. A crosswind is blowing due east at 44 meters per second. What's the plane's resultant velocity relative to the ground? Hint, I wrote, write an equation, then DOLP. If you look at your formula sheet, you will notice in this unit, I gave you an equation that looks like this. I think it says V, and then what did I put as a subscript? Airplane or engine? Can I just put an E for it because I tend to abbreviate? Plus V wind gives you V ground. What you want to imagine is this airplane is flying due north. Here's the pencil pointing. It's flying due north, but a wind is blowing to the east. So if I stand like this, if you look at the shadow, the plane is going north, but the wind is pushing it that way. And so its path on the ground will be something like that. It will be moving north and east at the same time. This is hugely important in, for example, if you're becoming a pilot. Although I think now it's all computerized and automated, but certainly 40 or 50 years ago, before GPS became prevalent, you had to do this by hand, or you had to calculate this. You had to know what you're doing. And I suspect they still make you learn it just in case the GPS system fails. So the engine speed, which way you're pointing the engines, plus the crosswind, that's what gives you your ground velocity. By the way, in the industry, if you do become a pilot, they call it ground speed. It is a vector. They should call it ground velocity. I'll call it ground speed because that's what they call it in the industry, even though that's fingernails on the blackboard irritation to me because it's a vector. So there's my equation. Now DOLP. What's the engine velocity? Which way is the plane pointing its engines? Which way is it flying? How big? So I'm going to draw an arrow pointing north, and this is 132 plus. Aman, which way is the wind velocity? How big? Doing some quick math, 40 is roughly 1/3 of 130. It's 1/3 of 120. So I'm going to draw it fairly short. Yoink. 44. Aman, I'd like to add these two vectors together. Any thoughts on how I might want to draw them? Now, this here is not good scale. I'm going to, when I draw my triangle, make the 132 longer so it's more obvious. And then there's the 44. Again, though, you could have drawn the 44 first. and then the 132. We'll get the same answer, same magnitude. You'll just get a different theta, but it will be the same direction. The resultant is from the tail of the first to the tip of the second. So this here is the ground velocity. And then where is theta going to go? Always where the vector is originating from. So is theta going to go bottom left or top right? Right there. Got the setup? Good, solve this on your own. I'm not going to freeze the screen this time, but I'm not going to talk you through it. I'm just going to do it. By the way, in real life, that expression isn't true. Although one did become president. Never mind, that slipped out. Maybe that's the exception that proves the rule. Yeah, so Mason, don't try and memorize patterns that aren't there. Yeah, again, the small numbers on top. That's just because typically the wind is blowing less than the plane is traveling in real life. So if you're looking for what kind of a word problem that I might throw at you on a test, this will be a good one. Crosswind is a nice application. Or, we haven't done this yet, I might tell you the wind, tell you the direction that we want to go, and ask which way should we point the plane. That's a much more useful question, because usually when you're flying a jumbo jet, you know where you want to go. You have the weather forecast for the wind. Okay, which way am I pointing so that I go in a fairly straight line? Okay. I ended up using tangent. By the way, once you do Pythagoras, you have this answer, which means you could also use sine or cosine, except I rarely do, just because in case I got that wrong, I can still get the what of what and the theta right by using the data that they gave me. But once you have this number, if you put it there to like 5 or 6 decimal places, you could use sine or cosine to get angle theta as well. How do you add two vectors together, Jabber? Draw them. How do you add two vectors together? Draw them. How do you add 3 vectors together? Well, you don't. In the same way you don't add 3 numbers together. If I go, don't write this down, don't write this down. If I go 3 plus 6 plus 8, you always add 2 numbers, get an answer, and then add the next. There is no algorithm to do all 3 magically at once. So 3 forces, how do I add 3 forces together? I'll add 2 of them, then I'll add the third. However, we can be clever. Look up. If I was going to add 5 plus 7 plus 5, what would the clever, easy way to do this be? Do the 10 and then add the 7 to go 5 plus. So since order doesn't matter, sometimes there'll be an easier way to do things. 3 forces are acting on an object. F1 is 5.5 newtons south. F2 is 8.6 newtons west. F3 is 10.6 newtons south. What's the net force, or what's the resultant? Because that's really what a net force is. When we were going winner minus loser equals F net last year, what we were really doing was vector mathematics and finding a resultant. Dolp. Okay. I've scrolled down, so I'm going to do a compass rose because I've botched that many, many times. Also, that ties into my whole, I like to write something down. I feel better because now the juices are flowing. I'm going to do better. South, 5.5. Plus. West, 8.6. I drew it longer than the 5.5. Plus. South, 10.6. I drew it longer than the 8.6. What would be the smart order to do this question in? I can't hear. I think you're right. Yes. And even if one of them had been north, I would still do that first. I would do the stuff in the same direction of plane first, and then add the third one in. So, in fact, I think I can do this in my head. 5 plus 5 south plus 10 plus 6 south, 16.1. Yeah? So I'm going to put a little equal sign. This is 16.1 plus 8.6. I've changed the scale here, but I know that 8.6 is roughly half as big as 16.1, so I drew the 8.6 roughly half as long. And now I can add these two together. And if I want to add these two together, how would I draw them? Tip to tail. And you can either go 16.1 down and then 8.6 left, or you can go 8.6 left and then 16.1 down. And you can start to see why it might be handier, depending on how much room you have on your page, to go in one order or another. But if you have a choice, go in the same order that I've written them, because that way all of our diagrams look the same. So I'm going to go 16.1, 8.6. There is the resultant. I'll call it force R for force resultant. I haven't left myself much room. Well, no, I think I can fit the work right here. Now, you'll notice I've stopped showing the Pythagoras work. I'm doing it all on my calculator. I'm okay with that. So, force R has a magnitude of Oh, where's theta going to go? Bottom left or top right? Top right, where it's coming from. And there's my 90. Color, 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 color. Mr. Dueck, is it always tangent? Only in the nice examples, Mason, that I'm making up today. Okay? And it'll usually be tan, but not always. Yeah. Yeah, except if I got this wrong, then I'm going to get that wrong. So I'm avoiding using a possible wrong answer to find a possible wrong answer. I'll use what they gave me. But absolutely. Now, if I had extra time and this is an actual test question, what I would then do is I would use these two to find theta. And if I got the same answer of 28.1 degrees, then I know I did the Pythagoras right as well. Yay! Because there's no way I could have fluked out and gotten the same angle. Liam, how do you add two vectors together? Draw them. Mason, how do you add two vectors together? Draw them. Kenley, how do you add two vectors together? Draw them. How do you subtract two vectors? We'll talk about that next class. I love Foxtrot Comics. The author, Bill Ammond, actually has a physics degree. When he was in university in his physics classes, he was doing a lot of doodling, and his friend said, hey, those are funny, you should publish them. And so he's become a full-time comic strip publisher. But The young boy in the family, Jason, is a physics nerd. I relate. So Jason is playing football with his older brother, and it says this: Jason, what pattern did I tell you to run? You said go 10 yards out, then 10 yards to the right. And what pattern did you run? Well, I went 10 root t yards at a 45-degree angle. Rather the same thing? Well, if you add the vectors, sure. This is football, not math class. Why do you think I rounded to 2 decimal places? Once again, they're playing football. It says this: okay, here's the play. Go 40 yards downfield, then turn left and go 20 yards, then turn right and go 25 yards, then turn right again and go 30 yards, then turn right and go 30 yards, then turn left and go 10 yards. Then turn left and go 15 yards, then turn left and go 20 yards, then turn left and go 50 yards, and I'll hit you with the ball. Peter thinks for a while. Won't I be right back where I started? Jason says I can't throw very far. We have, on a nice sunny day, gone out into the field and run this play. The vector math works. You do end up with a resultant of 0. You do end up right back where you started from. And that's one of the other reasons I like Foxtrot, is he's careful with the math. Good comics. What's your homework? I'm not actually going to give you a sheet on vector operations. Your homework is to make sure you have the trig done from last day. And we're going to pick up with this next class.